Greetings, everyone. I hope you're doing well. As I record this, it is a beautiful April day. The sun is shining, the sky is blue, the flowers are blooming, and I'm actually looking out a window, which wouldn't be happening if I was at school. So, hey, we got to count our blessings where we can find them, right? So, before we take notes on today's lesson, there are a couple of pieces of background information that I want to remind you about that are definitely going to come into play here. So first of all, when we studied chapter 4, the first thing we went over was inverses. And if you want to pause and grab your notebook and look back at notes number 22, you will notice some key points we learned about inverses. Inverses have x and y coordinates switched. Inverses are reflections across the line y equals x. Those are the main key points that we're going to be using today. And when we say that they have x and y coordinates switched, that can extend to the idea that they have domain and range switched. So the domain of one function is the range of its inverse, and the range of a function is the domain of its inverse. So that's going to be important as we learn new information today. By the way, do you realize that notes number 22 was the start of the unit we did in our flipped classroom model? And oh, if we ever knew then what we would be doing now. It's kind of interesting. I reflect on that sometimes. No idea that that was going to help prepare us for today. Okay, here's another piece of background information that we're going to draw on. So if you look now at notes number 30, this was our first day of trigonometry, and we were starting with basic trigonometry, looking back at what we knew from geometry. And these were a few of our examples. So in example number 8 right here, we wanted to find a missing side length, and we knew an angle and we knew a side, and so we used the sine ratio, the sine of an angle, and that gave us the ratio of opposite over hypotenuse. So when we use sine, we input an angle and we output a ratio. Then in number 10, it was the reverse situation because we didn't know the angle and we knew the sides and we wanted to find the angle, and we ended up using inverse sine. So remember, we use inverse sine if we don't know the angle. We input the ratio, we output the angle. So let me say this again. In regular sine, input the angle, output the ratio. In inverse sine, input the ratio, output the angle. Do you see how those have switched there? Because we're talking about inverses. And similarly, we did a problem where we used the tangent ratio. We knew the angle, and that was our input, and our output was a ratio. We did another problem where we didn't know the angle, and we used the inverse tangent. We input the ratio, we output the angle. Okay, so hopefully we're getting this point here that I'm trying to make, because today we're going to be looking at the graphs of inverse trig functions and how we use inverse trig beyond just a right triangle. That's a lot of what we've been doing in this unit, is learning how, or in this semester really, is learning how we use trig beyond just the simple right triangle. So I think this is notes number 45, inverse trig functions. We'll spend a couple of days on this topic. And the first thing we want to do is just think about what we know about trig functions. We input an angle, whether that angle is in degrees or radians, it's an angle, and we output a ratio. You could say we output an exact value, we output a number. It might not look like a ratio, but basically it's a ratio. An example of that would be sine of 30 degrees equals 1/2. We input 30 degrees, the angle, we output 1/2, the ratio. So then, if we are going to find the inverse of trig functions, we're going to switch x and y, we're going to switch inputs and outputs, domain and range, and we input the ratio and we output the angle. Here's an example of what that might look like. The inverse sine of 1/2 is 30 degrees. Notice the relationship between these two examples. You input the ratio, you output the angle. Now here's the tricky thing. There are actually a lot of different angles with the same sine value, a lot of different angles with the same cosine value, etc. So that creates an issue of not having a function, because as you know, for a function, every input has only one output. So what we're about to see is how we resolve this issue of having multiple outputs for our inputs. Okay, this might be a little blurry. Sorry about that. I just wanted to take advantage of the slides I already had made. So, picture your regular sine graph. It would keep going sideways, you know, on and on forever toward infinity and negative infinity. This is just a little bit of it. So because we know that it keeps going, its domain is all real numbers, negative infinity to infinity. And for its range, the y values it goes through, you see that it has a minimum y value of -1 and a maximum y value of 1, so the range is -1 to 1. Now, what would happen if I took that function, let me even draw it a little bit more extreme. What would happen if I took that function and I reflected it across the line y equals x to get its inverse? Can you picture that? If I do that, 0, 0 is still going to be at 0, 0, but then we're going to have something that looks like this. Now that is going to fail the vertical line test, right? It's going to fail the vertical line test horribly, and that's not a function. So, do we even care? Well, mathematicians tend to care that things are functions. Functions behave in a particular way. So what we do is we limit the range so that we can have a function. So here's what that looks like. Okay, we had our sine graph. It went on and on forever sideways, but we're just going to restrict it to a single piece, a small piece that is 1-to-1. That means a small piece that passes the vertical line test. I don't remember if we talked about the phrase 1-to-1 when we did that chapter, but passes the vertical line test, okay, and the horizontal line test. That's the most important part because the other one passed both the vertical line test, but we want to pass the vertical line test and the horizontal line test. 1 x for each y, 1 y for each x. Okay, so for this piece, what's the domain? Well, we see that it's going from here to here. That would be -pi/2 to pi/2. So that's the domain of that piece. If you want to think about that in terms of degrees, we're talking about -90 degrees to +90 degrees. What's the range? Well, you can see it still goes from a height of -1 to a height of 1. Now, if I take just that little bit of the sine graph and I find its inverse, I will get something that is a function. So this is what the inverse sine graph looks like. It's just a piece of the sine graph that has been reflected across the line y equals x. So now the domain will be what the range of sine of x was. So the domain is -1 to 1. And the range will be what the domain of the sine graph was. So that would be -pi/2 to pi/2. That means the outputs will be numbers that fall between -90 degrees and +90 degrees. Those would be angles that fall in quadrants 1 and 4. So even though there might be infinitely many angles with a particular ratio, we're only going to answer the ones that fall in 1 and 4, between -90 degrees and 90 degrees. Okay, we have inverse trig functions like this for all 6 trig functions, but we're only going to do 3 of them this year. So we have inverse sine, inverse cosine, and inverse tangent, and we're just going to have to let go of the other three, but the concepts apply the same way. Okay, so let's move on to the cosine graph. So we know what cosine looks like. It would continue on and on horizontally, and its domain would be negative infinity to infinity, and its range would be -1 to 1, just like the sine graph. So, just like with the sine graph, we're going to have to limit it to just a small piece if we're going to find an inverse of it. So the piece that we limit this one to, because it has to be 1 to 1, for every x there's only one y, for every y there's only one x, the piece that we limit it to is this piece that you see right here in this graph. So that goes from x equals 0 to x equals pi. So the domain is 0 to pi. And it goes from a height of -1 to a height of 1. So the range is -1 to 1. Now we can take that piece, we can reflect it across the line y equals x, and we will have the inverse cosine graph. All right, it ends up looking like this. So that's what inverse cosine looks like. By the way, when you see the word inverse cosine or the symbol inverse cosine of x, it's equivalent to arc cosine. Sometimes they use arc cosine. That's a bit of an archaic, get my pun, archaic way of doing it. But sometimes it's handy because this -1 here, it kind of looks like an exponent. That could be confusing. If you write it as arc cosine, then you don't have anything that looks like an exponent. Another way it's sometimes written is just like this, inverse cosine. And the same thing would apply for any of the inverse trig functions. You might see arc sine, arc cosine, arc tangent, etc. Okay, so here's the graph of the inverse cosine. And so the domain and the range will be the reverse of what they were for cosine. So that means the domain goes from -1 to 1. And the range goes from 0 to pi. So numbers from 0 to pi, if you think of them in degrees, those would be numbers from 0 to 180 degrees. And so those would be numbers from quadrant 1 and quadrant 2. So your outputs are going to be angles in quadrant 1 and quadrant 2, just between 0 and 180 degrees. Okay, now let's take a look at what we do with tangent. So we know that tangent has all these repeated increasing curves going on and on forever. Its domain is not all real numbers because there's certain numbers where it's not defined. Everywhere we have a vertical asymptote, it's not defined. So we have everything but pi over 2, negative pi over 2, 3 pi over 2, etc. So x is not equal to pi over 2 plus pi times n. That will allow us to add a pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. And what about the range? Well, it goes from -infinity to infinity. So what we need to do then is take just a piece of this graph, and that piece will be what we find the inverse of. So we're restricting this graph to just the middle piece. That would be the most convenient. And this piece is 1 to 1. Every x has only one y, every y has only one x. It passes the vertical line test, it passes the horizontal line test. So the domain of this piece would be negative pi over 2 to pi over 2. We don't include the endpoints in this case because that's where we have the vertical asymptotes. So round brackets not square on that domain. And then the range is still all real numbers. Okay, so we can take this piece and we can reflect it across the line y equals x to get the inverse. And it is going to look like this. Oops, let me try that again. Kind of like that. There's not supposed to be a hole in it. That's just because my stylus isn't working very well. Okay, kind of like that. With a horizontal asymptote up there and a down there. Okay, And so where were the vertical asymptotes of tangent? They were at negative pi over 2 and pi over 2. So that's where the horizontal asymptotes of inverse tangent are going to be. So the domain is going to be the range of tangent. So that was negative infinity to infinity. And the range will be what the domain of tangent was, and that would be negative pi over 2 to pi over 2. Okay, you can think of that in degrees, negative 90 degrees to 90 degrees. So we're outputting angles in quadrants 1 and 4. Now, this all seems very abstract right now, probably. Don't worry about memorizing what these inverse trig graphs look like. The most important thing is that you understand the basic idea of inverse, that for inverse trig, you're going to input a ratio and output an angle. In fact, if you want to even abbreviate that, just think of it this way: inverse trig, output an angle. And that's the most important idea. And let's go ahead and do these examples. Okay, so for the first set, we're going to answer in degrees and radians. And in your book, you'll just have to follow the directions they give there. When they say find the exact value, they mean find radians. And then when they want degrees, they'll say find degrees. Okay, so number 1a, we're finding y. Y equals arc sine of square root 3 over 2. That means find the angle with the sine value of square root 3 over 2. And remember, for inverse sine, this has to fall between negative 90 and positive 90. So you ask yourself, here's the process. You ask yourself, what quadrant would it be in if the exact value was square root 3 over 2? Notice that that is positive, so that would be quadrant 1. Now we know that sine is also positive in quadrant 2, but we're not using quadrant 2 for inverse sine. We're only using answers that fall between negative 90 degrees and positive 90 degrees. So quadrant 1, the sine is the opposite over the hypotenuse, so you can label the sides. And now, can you tell what angle that is based on all your experience with those triangles? Hopefully you can tell that that would be a 60-degree angle. And then we're going to answer in radians as well. So we can say that y is 60 degrees, and in radians, y is pi over 3. That's how you do that problem. It's just working backwards. Part B, y equals inverse sine of negative 1/2. So find the angle with the sine of negative 1/2. Because it's negative, we're not in quadrant 1, we're in quadrant 4. Now we know that sine, typical sine, is negative in quadrants 3 and 4, but we're doing inverse sine and we're restricted only to angles between negative 90 and positive 90. So only quadrant 4 for the negatives, quadrant 1 for the positives. So let's draw that. Quadrant 4, sine would be opposite over hypotenuse. Hopefully now you realize what triangle that is. That's your 30, 60, 90 with a 30-degree reference angle. Typically, we would answer that the answer is 330 degrees because we are used to going all the way around counterclockwise. But for inverse trig, we were told your answers have to fall between negative 90 and 90. So we're going to answer that this is negative 30 degrees. And that would be, in radians, negative pi over 6. Okay, let's do another one. Y equals inverse sine of square root 2. Okay, so find the angle with a sine of square root 2. Now, you can make that into a fraction, square root 2 over 1. Notice that it's positive, so that would be quadrant 1. Draw the triangle. Opposite, square root 2 over hypotenuse 1. Now, do you realize we have a problem? Square root 2 is approximately 1.4. How could it possibly be longer than the hypotenuse? What do you think? This is not possible. It's not possible for a sine value to be greater than 1. Tricky, tricky. Okay, let's do a couple more. Same idea. Find y in each equation, answer in degrees and radians. Y equals arc cosine of 0. Okay, the angle whose cosine is 0. Ooh, 0. Now we have to switch our thinking and think about quadrantal angles. Okay, now where is the cosine equal to 0? And we have to answer between 0 degrees and 180 degrees, or between 0 radians and pi radians, because that was our restriction for inverse cosine. So right up here, at this point, 0, 1, the cosine value is 0. I should write what we're thinking here. We're thinking find the angle with a cosine of 0. Okay, so that angle is 90 degrees. And if we want to put that in radians, we have pi over 2. Next one, find the angle whose cosine is 1/2. One half is positive, cosine is positive in quadrant 1. Draw the reference triangle in quadrant 1. Try that again. Adjacent over hypotenuse, 1 over 2. Okay, so there's our 30, 60, 90. And so we know that that one's going to be a 60-degree reference angle. And so the angle is 60 degrees. Or if we put that into radians, we get pi over 3. Okay, let's do one more. Find the degree measure. This time they don't ask us for radians, just degrees. And this one is arctangent, inverse tangent. So inverse tangent of square root 3. So find the angle. Goodness, I'm having technical difficulties all over the place. Find the angle with a tangent. Sorry about my handwriting. Doing my best. Find the angle with a tangent of square root 3. So let's make that a fraction, square root 3 over 1. That's positive, so it would be in quadrant 1. Notice that these are all positive in quadrant 1. If they're negative, then we're going to use quadrant 4 for sine, and inverse tangent, quadrant 2 for inverse cosine. Draw the reference triangle. Tangent is opposite over adjacent, so square root 3 and 1. So there we have that same triangle again, 60-degree angle. So theta is 60 degrees. So that's how we do that kind of thing. That is your introduction to inverse trigonometry. I hope that made a little bit of sense, and I hope you'll ask me questions if you are confused about anything. For your assignment, we have just these little short problems to do, so I gave you, about 12 of them or so. And there will be a video of the solutions worked out and talked through in case you need some help. Thank you, everybody.